Alright, this is the second hour of Physics 1B for September 29th. So now what we're going to do is we're going to solve quite a few different problems involving the equation of specific heat, so we can get an idea for how it's used and how you're going to see it show up in your homework problems. So let's get started with that. So that's our specific heat equation. We're going to go through kind of just increasing levels of difficulty. We'll start off with something really simple. Then we'll add like a little crinkle and we'll just keep going until we're doing some calorimetry problems. Alright, so it says, during a bout with the flu, an 80 kilogram man, well that's a mass, ran a fever of 39 degrees Celsius instead of the normal body temperature of 37 degrees Celsius. If we assume that the human body is mostly water, how much heat is required to raise his temperature by that amount? Alright, so our goal is to solve for heat here, so this is a direct plug and chug kind of equation. The other piece of information that we're going to need is that the specific heat for water is about 4190 joules per kilogram Kelvin. And in this problem, we also know that the change in temperature, delta T, is going to be equal to delta T. It looked like dt. Delta T is going to be equal to 2 degrees Celsius, right? Because it's going from 37 degrees Celsius up to 39 degrees Celsius. So that's a change of 2, positive 2. So if we plug those pieces of information into our problem here, we can actually figure out exactly what the amount of heat that was required to raise his temperature by this amount. Where would all that heat be coming from? Do you have any idea? Where does all the heat come from whenever you're sick? You have a cold or a flu or something like that. Does anyone know? Your cells? That seems like a reasonable answer. Your own immune system. I think that's right, Ariana. Yeah, it's fighting the infection, and that generates a lot of energy, a lot of heat. Okay, so that's my understanding. I could be wrong. I always assume that you're all way more intelligent than I am when it comes to stuff like biology, because I know very little about biology. Alright, what's this going to be equal to? This is like something like 8,000 times 80. It purposely raises the temperature to cook the virus. Oh, that's cool. So if we calculate this, what are we going to get? Let's see that. 84 times 8. It's going to be like 160k, something like that. What do you get if you calculate that? Okay. That was way off. Is that really what it is? Oh yeah, 8 times 8 is 640. Right. 670k. We'll just say 670 kilojoules. How about that? Really easy problem. We're just trying to use the equation. That's it. Given a temperature change, given the type of substance, in this case we're treating the body as mostly water, and we got the mass, so. Any questions? Okay. Let's do something a little more challenging. So, this next problem, I'm going to mention something that I'll pull this down here and we'll talk about it. So there's two pieces to this equation right here. Let me make this a little bigger to make sure everybody can see. There's this version, but then there's this version right here. It says the specific heat has different, okay, whatever. For an infinitesimal temperature change dt and corresponding quantity of heat dq, we have this relationship, okay? Where we say that if we look at very small temperature changes, we should be able to use the equation like this. We're going to see this happen a lot later on in this class, when we're talking about systems that we want to gradually raise the temperature very slowly, so the temperature change is going to come in little tiny intervals. So what's dt? dt is like a tiny temperature change. Okay? It could be like, dt could be equal to something like, I don't know, 1 nanokelvin or something like that, or 1 millikelvin, centikelvin, something like that, right? dt would just be like a really tiny temperature change, right? And corresponding to that would obviously be a very tiny amount of heat that gets transferred. So this next problem shows how we can use this concept to solve a problem that involves a heat change that's taking place over a long period of time. So let's look at it. Overheating electronics. Anyone in here who's dealt with electronics in any way, if you own a phone, a computer, a laptop, anything like that, you know that electronics tend to heat up, especially laptops, right? You get too many applications or things running on your laptop. Laptops have a very, very difficult time dumping their heat, right? I mean, my PC that I'm working on right now, it gets hot, but it has a nice cooling system inside of it that allows it to get rid of the heat. It generates heat, but it can get rid of the heat, right? It's a big problem with electronics. So it says you're designing an electronic circuit element made of 23 milligrams of silicon. Okay, so 23 milligrams, that's going to be a mass. Is that right? MacBook Pro with the M1 chips? That's interesting. Yeah, Macs are always doing a really good job of staying at the cutting edge, right? So they don't heat up very much, huh? What if you try to run a game like Civ 6 on it, though? I bet it'll heat up then. Maybe I'm wrong. I don't know. Anyway, my computer gets crazy hot when I play like really modern video games. It's just out of control. The fan just like blows really hot. Anyway, so we have electronic circuit made of 23 milligrams of silicon. The electric current through it adds energy at the rate of 7.4 milliwatts. So just W, if you don't remember, 1 watt is a joule per second. So the electric current through it adds energy at the rate of 7.4 milliwatts. If your design doesn't allow any heat transfer out of the element, which is kind of ridiculous, but whatever, at what rate does its temperature increase? The specific heat of silicon is 705 joules per kilogram per Kelvin. I hate the way they write this. I mean, just from like 6th grade mathematics, like this says joules per kilogram times Kelvin, right? Like this isn't right? Do y'all agree? They should have like parentheses around these things. I hate that. It's so lazy. It's confusing too, to be honest. Anyway, so all we have is a mass, and we're given a rate of heat transfer. It says it adds energy at the rate of 7.4 milliwatts, which they say is 7.4 times 10 to the negative 3 joules per second. Now this is a problem where it's really not obvious. If all you do is look at this equation, it's not obvious at all what we need to do. So let's look at it and let's talk about what we know and what we don't know. Well, first of all, we know it's silicon, right? And they give us the specific heat right here. So the specific heat of silicon is 705 joules per kilogram Kelvin, right? So we have C. Oh, that shouldn't be delta. That should be a D now. My bad. Sorry, that should be dt. And what we know is that there's this rate of energy transfer. So what can we do to our equation to get some information about how to use this quantity here? What's that going to be? It's obviously not mass. It's obviously not specific heat. So it's going to have something to do with either the dt or the dq, right? What's it going to be?
dq?
dq, yeah. Now, dq would have units of joules, though, right? And this has units of seconds. So we definitely need to divide by time, right? Now, we could just divide by time like this. But, usually in problems like this, they love to divide by dt, just to confuse you. Maybe it's not confusing. I don't really know. Basically, we divide both sides by dt. Then we'll get dq over dt, which will have units of joules per second. This would be the rate of energy transfer, right? So that's what this is going to be. It's going to be the rate at which heat is increasing, right? And then dt over dt is going to be the rate at which the temperature increases, right? This is going to be the rate at which the temperature increases. And that is what we want to figure out, because it says if your design doesn't allow any heat transfer out of the element, at what rate does its temperature increase? So we want to solve for this. So we'll do that by taking our dq over dt, dividing by mc, and that should be equal to the rate at which the temperature increases. And if we plug in those numbers, so we have in the numerator 7.4 times 10 to the negative 3 J over S. The denominator mass was 23 milligrams, which would be... We have to convert it to kilograms, right? We have to convert it to kilograms. So I think it would be 23, and we need to divide by 1,000,000. Right? Because 23 mg, get two conversion factors here, you'd have to have, there are 1,000 milligrams in a gram, and there are 1,000 grams in a kilogram. So that would give us 23 times 10 to the negative 6, not 2.3, 23 times 10 to the negative 6 kilograms. And then we multiply by the specific heat here of silicon. And we will get the temperature increase in kelvins per second. Because the joules will cancel, these kilograms will cancel, the Kelvin will get flipped to the top. So our answer is going to have units of Kelvin per second. Which is the same thing as degrees Celsius per second. What do you get if you calculate that? That's what I got to, Louis. 0.456 Kelvin per second. Now, if you think about this, this quantity is a massive temperature increase, right? Imagine something increasing its temperature at half of a degree every second, right? After 2 seconds have passed, it's increased its temperature by 2. After 100 seconds have passed, it's increased its temperature by 50 degrees Celsius. 50 degrees Celsius is hotter than any place on the planet. You know what I mean? There's no place on our planet other than like inside of a volcano or something like that, or inside the core, where the temperature is 50 degrees Celsius, right? So even if it started at like 0 degrees Celsius, after less than a minute, its temperature would be 50. And if you waited a few minutes, its temperature would be like really hot. You wait a few hours, its temperature is going to be like the temperature of the sun. So there's obviously some ridiculous things going on here because, you know, if something's temperature increases this quickly, the whole system is just going to melt, basically. Something you might see when you take 1C. When you take Physics 1C, some of the labs you do, you hook up some electrical components and stuff like that, and the electricity starts to flow, and maybe you make a mistake and the electricity flows too fast. The wires will literally burn in front of you. It doesn't take much. When it comes to electricity, temperatures can increase super, super fast. Now, this is a little bit ridiculous in terms of the assumptions here because it said that if your design doesn't allow any heat transfer out of the element, that's ridiculous. Because every system is going to have a rate at which it's going to lose, you know, it's going to lose energy to the environment, right? And almost all electronic devices are designed to be able to dump out their heat. And the way in which they do that is, well, usually by having something like, you know, in computers, there's something called a heat sink, and what it is basically just a bunch of blades of metals that have really large surface area that can basically, think of it as like, they can like evaporate their heat into the environment. And then of course also things like fans. Nowadays, a lot of computers use liquid cooling, right? Because...
For the lab?
Huh?
For the labs for 1C,
yeah.
how much current is it? Like 12 volts?
Well, so 12 volts is a measurement of voltage. Current's measured in amps. That's okay. No, it's what happens is that when the current gets really big, the system can start to burn. Because literally what electric current is just the flow of electrons. And if they flow fast enough, they heat things up really fast, just like anything, right? Anything that moves quick is going to heat up. The tires on your car, when you drive down the road, those things heat up really fast, right? Anything that has a lot of...
Yeah.
Your engine obviously heats up really fast. Of course, there's an explosion going on inside of most engines too, but regardless. So
is there like a standard electricity voltage that you guys are using for 1C?
There's a lot of different versions that we use. Like some of the labs use like just simple batteries that have 1.5 volts. One of them has... I'd have to look in the manual. I know there's one that we do that has an extremely high voltage. Like either in the thousands or the hundreds of volts. I don't remember what the number is off the top of my head though. But
that's in the future, right? For 1C?
Yeah, in 1C. In this class. Transformers are definitely things that can heat up really fast. Transformers are these devices that basically convert really high voltage down to low voltage. so you can use it in
And they
your
have to
home.
release heat, though, right?
What?
They have to release heat somehow.
The transformers? They do, yeah, exactly. Because they can get really, really hot. And if they get too hot, they will pop and they will explode. And that can happen. I don't know if it happens so often around here, but like where I lived, which I know you don't all have a lot of experience with this, but like in Oklahoma, when it gets super, super hot in the summertime, it is really common to get power outages because transformers will explode. Anyway, international converters. Yeah, those things can heat up a lot too, right? It's actually the same. It's the same thing as a transformer, as it turns out. A transformer and the internet, they're basically the same object. Just coils that use induction to step up and step down. They changed. Yeah, they can increase or decrease current, basically. And they can decrease or increase voltage. But it always comes at a cost. Like, the relationship between current, voltage, and power is equal to current times voltage. So if you increase the voltage, the current has to go down. If you increase the current, the voltage has to go down. So you can't increase both at the same time. You can't get something for free. And there's also losses and stuff like that. But yeah. All right. And of course, that's important because certain devices only operate off of like 12 volts. They don't want all the voltage that's coming out of the wall, which might be 110, stuff like that. All right, let's keep going. Next thing I want to do is to talk about calorimetry. And the best way to talk about it, I think, is just to do some problems with it. But in general, I'll give you a summary of how we approach these problems. All right. Calorimetry is a phrase we use to describe physics problems that involve heat changes and have multiple substances like ice, water, metal, copper, all kinds of different things mixed together in a certain situation. And you want to figure out what the total heat transfer is and use that to find information about what's going on. The equation we use for this is when you have multiple heat transfers in a system, the total sum of heat transfers has to add up to 0. So heat's going to flow from one object to another object, and we have to say that when I add up all of the heat transfers that occur inside of a closed system, I should say in a closed system, and a closed system is basically going to be a system that is not allowed to exchange heat with its environment, which again is a pretty ridiculous assumption, but this can be actually reconstructed in a lab pretty easily. A closed system would be like the inside of a styrofoam container, like a styrofoam cooler. Styrofoam does a really good job of preventing heat flow in and out of it. So if you dump a bunch of things into a styrofoam cooler, you can make sure that it was a closed system. And you could figure out the heat transfer. So a common question with calorimetry might be like, let's say I take a styrofoam cooler. Let's say that I throw a kilogram of ice in there, right? And then I take water at room temperature and I pour the room temperature water of maybe I pour a few kilograms of room temperature water in there, and then I close the system off. And I ask, give it enough time, let's say an hour passes, what's the final temperature of the system going to be? That's a common kind of calorimetry kind of question. So the best way to talk about this, I think, is to just do an example problem. If you've taken chemistry, you almost certainly have seen problems like this before. I'm not sure if the way that they solve them in chemistry is the same, but I'm pretty sure they are. So if you have taken chemistry, this portion of this class should be pretty easy for you. Assuming you understood it when you learned it, I don't know. So it says, a camper pours 0.3 kilograms of coffee initially in a pot at 70 degrees Celsius into a 0.12 kilogram aluminum cup, which is initially at 20 degrees Celsius. What is the equilibrium temperature? Assume that coffee has the same specific heat of water and that no heat is exchanged with the surroundings. Right? Closed system corresponds with no heat is exchanged with the surroundings. The same idea. Right? So what we have here is coffee being poured, right? And it's poured into a cup. So let's draw a cup right here. So here's our cup. And we're pouring coffee into it. We use this darker color here for coffee. So we have coffee in here. And what we know is that initially, the initial temperature of the coffee, we'll say T initial for the coffee was initially 70 degrees Celsius. Camper pours 0.3 kilograms of coffee, initially in a pot at 70 degrees Celsius, into a aluminum cup with this. So the initial temperature of the coffee is 70. And the initial temperature of the cup is 20. So here's our cup. It is a aluminum cup, right? So we'll say the initial temperature of, do I want to say aluminum or cup? We'll say aluminum. The initial temperature of the aluminum is going to be 20 degrees Celsius. And then we're assuming that there's no heat exchange with the surroundings. So you'd have to enclose this entire thing with styrofoam or something like that. So it's in a closed system, so it can't heat up from the surroundings. Is that hard to imagine? Say we just take the whole thing, we put it into a styrofoam cooler. That's basically what this means. Just encase the whole thing in styrofoam so that none of the heat escapes. No heat comes in, no heat goes out, okay? So that this little yellow line here is going to be like a closed system. No heat goes in, no heat goes out of this yellow line. But, of course, the coffee can heat up the aluminum, which it should, right? It has to, right? Coffee's hotter than the aluminum. They have to come to the same final temperature, basically, right? And that's what we're looking for. It says, what is the equilibrium temperature? We have a couple other pieces of information here that we should write down. We also know that the mass of the coffee that we're adding, mass of the coffee is 0.3 kilograms. And the mass of the aluminum that we have in the cup is 0.12 kg. And all we need to do is to sum heat transfers and say that they add to 0. Some will be positive and some will be negative. The way I'm going to write that is to say if I take the heat transfer of the coffee and I add to that the heat transfer associated with the aluminum, that this should be equal to 0. And for each one of these, we're just going to use the MCAT equation, the MC delta T equation. For this one, it's going to be mass of coffee times the specific heat of, well, they're saying treat the coffee like water, right? So we'll use the specific heat of water. And then delta T for the coffee. And this should be equal to, I'm running out of room right here. Let's go down here. So mass of the coffee times the specific heat of water times the change in temperature of the coffee. This should be added to, whoops. Not equals. We're going to add to that the specific heat of the aluminum, or the MC delta T equation for the aluminum. Like that. And then we just solve for the information we want to solve for here, which in this case is, what is the final temperature? You know, both of them will have the same final temperature. So let's expand out these delta T's. So delta T coffee is going to be the final temperature of the system minus the initial temperature of the coffee plus delta T for the aluminum will be the final temperature of the system minus the initial temperature of the aluminum. And then all we need to do is to solve for the final temperature. In the interest of saving time, because I would like to get to what is definitely a harder problem at the end, what I'm going to do is I'm going to write down the answer, and I'm just going to have you all just check the algebra yourselves. Tell me if you think it's right. So what I'm going to do is I'm going to distribute through here. I'm going to have some terms that are negative that we know. We're going to add those to the right-hand side, and those are going to show up right here. And then we're also going to have some terms that are multiplied by T final. This plus this. Those terms are multiplied by T final, so we're going to have to divide those out, and they'll show up down here. Alright, that's a lot of algebra. I don't want to do one more step. It's just going to take too much time. You're all capable of doing this. But I'll stop for a second to let you catch up. And tell me, does that look reasonable to you all?
Yep.
Okay. and then we just plug the numbers in. I guess I can still write down here. So TF is M coffee was 0.3. C water is 4190. Specific heat of water is, you know what, I'm going to write this as degrees Celsius because that's going to be what we're going to be using. Okay, T initial coffee was 70. Plus mass of the aluminum is 0.12. And then specific heat of aluminum, it's not given, so we're going to have to look it up in a table. I think it was 910. Yep, 910 right here. Multiply that by the initial temperature of the aluminum, which is 20 degrees Celsius. These problems, while they do involve a lot of like numbers, there's no vectors or anything, so that's kind of nice. And then we multiply M coffee, C water, so that would be 0.3 kg, and then 4190 J over kg K degrees Celsius, and then plus 0.12 kg 910 J over kg degrees Celsius. And then we just calculate what that's equal to. I think the answer here is 66 degrees. I'm just going to go ahead and write that down, and then I'll try to do the calculation real quick. You got that too? You got 66 degrees? Okay.
Yeah, I got 66 too.
All right, so something to keep in mind here, by the way, is that you could do this in Kelvin. You get the exact same answer, actually, as it turns out. Okay, so let's just keep that in mind. In this particular type of problem, because it involves a change in temperature, it's okay to do it in Celsius. But if you wanted to convert this to 313 and convert this to 293 Kelvin, you get an answer, and it will be whatever this is plus 273, I promise you. I did that in my other class just to check to make sure, but I want to keep going here. Don't have much time left. Any questions? That is a calorimetry problem. Pretty much involves summing up heat transfers, and in this case that means you're summing up MC delta T's. Now, what happens when the object goes from like ice to water? If you go from solid to liquid, or if you go from liquid to gas? Well, that's where latent heat comes in. Latent heat is the hidden heat. Latent means hidden, or innate, or something like that. It's the hidden heat associated with a phase change. So, just as a way to introduce this to you, suppose that I tell you, I have two different scenarios here. I have two pots of water, okay? And in these pots, I have water. But in the one on the right, the water's boiling. And over here, we're going to have ice cubes in it. Okay, so this is ice water, meaning a mixture of solid and liquid water. And this is boiling water, which means it's a mixture of that's weird. It shows that I've selected this, but it didn't change it. So I've got some heat under here that's heating this up. Now what I'm going to do is I'm going to stick a thermometer in both of these. Okay, so we stick a thermometer in this one. We stick a thermometer in this one. And I want you all to tell me, what are the thermometers going to read? If I put a thermometer into ice water, what is it going to read?
It's a lot cooler than the boiling water.
Yep, it'll be cooler. What's it going to read? 0. The temperature of this, I guarantee you, will either be very, very close to or exactly 0, depending on how much ice is in there. Now, it depends on where you measure it, but if you don't have any ice at the bottom may be a little bit warmer, depending on what it's near. But most likely, it's going to be 0. Do I have any ice left in this? No, I don't. The boiling water, what's the temperature going to measure?
100?
100, yeah. Temperature here is going to be 100 degrees Celsius. Now, why is that? Well, it's because as long as there is still some liquid water in here, the highest temperature the water can reach before it boils, before it vaporizes, is 100 degrees Celsius, right? Now, when something reaches 100 degrees Celsius, all the water doesn't just instantaneously boil off, right? It takes time. It takes time for the water to completely boil off, right? And while that's occurring, during that time that you're adding heat, right? Without a doubt, we are adding heat. There's unquestionably heat is being added constantly when you put it on a flame, right? That being said, you're adding heat, but yet the temperature is not changing. It's not changing. So we'd like to be able to quantify a way to think about what's happening during this phase change here. We want to be able to talk about how heat can actually go into a system without a temperature change. Because when there's a phase change occurring, as long as you have a mixture of the two pieces of that phase, like when you have the solid and the liquid in the same place at the same time, or when you have the liquid and the gas in the same place at the same time, you're going to have the same temperature. And the way we quantify the amount of heat that's associated with this is through what we call latent heat. The equation that we use for latent heat is right here. I'm going to grab all of these. There we go. We're going to grab all of these. I hope we have time to do both these problems. I'll probably just do both of them anyway, just because I want to show them all to you. Alright, so this is our equation for latent heat. It's actually a pretty simple equation. It says that the heat transfer in a phase change is equal to Q times plus or minus M times L, where M is the mass of the material, just like Q equal to MC delta T. There's mass that shows up. And then L is a constant, which we call the latent heat for this phase change. It can be positive or negative. It's positive when heat enters the material. It's negative if heat leaves it. So it's positive when you go from like solid to liquid, right? It's negative when you go from liquid back to solid. Okay. Now, what is L equal to? Well, for that, we've got to use a table. We've got a lot of tables in 1B. In order to understand what the L represents right here, we come to this table. Let's look at just one portion of the table, which is water right here. We have the latent heat of fusion right here, the latent heat of vaporization right here. It has units of joules per kilogram. For water, the latent heat of fusion, this is when you go from liquid to solid or solid to liquid, is 334 times 10 to the third, or 334,000 joules per kilogram. That means that you need that much energy to melt ice. For every kilogram you have, you need 334,000 joules. Which again isn't that much energy, to be honest, because a joule is a really small unit. Once you want to go from liquid water into steam, you need even more energy. In order to convert a kilogram of water into steam, you need to input this much energy. You need to input 2,256, so about 2.2 million joules is what you need to input into the water to get it to convert to steam, which again, it sounds like a huge number. It's really not that much energy. What's bigger than joules? It's, joules is just what we use. So you have joules, kilojoules, megajoules. You could have, what's after that? Gigajoules. We don't have another unit of heat that's bigger than joules. Joules, diamonds. Yeah. So it's just, that's the cool thing about the metric system. Like, we don't have to have, in the English system, we have something like pounds and we have tons. Metric system, you just have kilograms and you've got megagrams and all that kind of stuff. Same thing with joules. Okay. Now there are, of course, other versions of energy. What are the other units of energy that we have? There's like the foot pound. There's BTU is a form of energy too, which maybe that's what you're thinking of. Pounds and tons. Yeah. Yeah, we don't have anything like that. The inch. What do we have? It's like inches, and then you have feet, and then you have yards, and then you have miles. Yeah, we've got a lot of them in the English system. Metric system, not so much. Okay, so given this idea, what we have here is a picture that's supposed to get you to understand exactly how this process occurs. So on this graph, let's take a second to look at the axes. I think one of the most important things about understanding what a graph says is to just focus on the axes first. So the y-axis here, you can see is measuring temperature in degrees Celsius. And it goes from negative 25 down here up to 125 right here. And the other axis right here is time. Okay? And in this temperature, it says heat is added to the specimen at a constant rate. So because heat is added at a constant rate, time is also a measurement of heat being added. Okay. So heat is being added as we move to the right, and the temperature of the system is going up, which is odd. That should be expected, right? When you add heat to something, you expect the temperature to go up. Except you'll notice here that there are places on this graph where the temperature is not changing, specifically right here at 0 degrees and right here at 100 degrees. There's a discrete change in the way that the graph looks. Okay? Because we're talking about water. And when I start off with, let's say, some amount of water at negative 25 degrees Celsius, it's going to be ice, right? That ice needs to heat up to 0 degrees Celsius before it can even start to melt, right? So that's what the portion of the graph is right here. You've got some ice, you're heating it up, it gets up to 0 degrees Celsius. Now, after it gets to 0 degrees Celsius, even as I'm adding heat, the temperature is not changing. Remember that as we move to the right here, heat has been added, but the temperature hasn't changed. But apparently enough heat was added so that the temperature can start changing again, which means between here and here, it's all liquid water, right? Between 0 degrees and 100 degrees, it's all water, liquid water. Now, once that liquid water gets up to 100 degrees Celsius, again, the temperature is not going to change. And it won't change until you've boiled all of it off. And then you've got steam, and assuming that it's all contained within a container, we can start increasing the temperature of the steam, right? There's a couple things you can notice about this graph when you look at it. The first thing that I notice is the energy we needed to actually convert the ice into water is very small compared to the energy we need right here, maybe a factor of 10. You almost need 10 times as much energy to actually boil water than you do to melt it. Also, you'll notice that the slope here is different from the slope here and the slope here. The slope for the ice is quite a bit steeper than the slope for the water. Why would that be? Why would the slope for the ice be different than the slope for the water? Does ice heat up more quickly than water does? Is that what it's telling us? Does ice heat up more quickly than water? Yeah, the specific heat of ice is lower, exactly. So the temperature change is always proportional to the inverse of the specific heat, right? And the specific heat for ice is something like 2090. And we know the specific heat of water is like 4190. These numbers might not be exactly right. Yeah, so it turns out that it's actually easier to heat up ice than it is to heat up water. Okay, so let's look at how we actually use these concepts in problems. We have 5 minutes left. I think I'll go over by like 10 minutes, and I apologize for that. We kind of started a little late, so. I'm recording, right? We are, okay. All right, a hot copper pot of mass 2 kilograms, including its copper lid, is at a temperature of 150 degrees Celsius. You pour 0.1 kilograms of cool water at 25 degrees Celsius into the pot, and then quickly replace the lid so no steam can escape. Find the final temperature of the pot and its contents, and determine the phase of the water, liquid, gas, or a mixture. Assume that no heat is lost to the Oh, wait a minute. I think one of the other problems got hidden, because this one's too hard. It's not too hard, it's just this is the hardest one. There it is. My bad. Apologize. We want to do this one first. It's a little simpler. Keep things simple to start, and then we make things a little harder. All right, here we go. Problem that involves changes in both temperature and phase. All right, a glass contains 0.25 kilograms of Omni Cola, which is mostly water, initially at 25 degrees Celsius. How much ice, initially at negative 20 degrees Celsius, must you add to attain a final temperature of 0 degrees Celsius with all the ice melted? Ignore the heat capacity of the glass. All right, so we have a glass. It is filled with cola. We're pretty much going to treat it as if it's water. It has a mass of 0.25 kilograms of cola. This is the mass of the cola. And it's initially at 25 degrees Celsius. So the initial temperature of the cola is 25 degrees Celsius. The question is, how much ice do we need to add? So we're going to add ice. Dump an ice in here. And the question is, how much ice do we need, the mass of the ice, if I know that the initial temperature of the ice is negative 20 degrees Celsius? How much ice do we need to obtain a final temperature of, what is it? 0 degrees Celsius. With all the ice melted. So we're going to assume all of the ice melts. That actually makes the problem a little simpler than it could be. Because if only some of the ice melts, well, it's a completely different kind of question. So this is another calorimetry problem where we're going to sum up all of the heat transfers, sum up all of our Q's, and say they have to add to 0. What are the heat transfers in this process? Can you all tell me? I believe there's 3 of them. Is Andrew talking? Go ahead.
Yeah, the glass, the cola, and also the ice.
We're going to ignore the glass, by the way, but yeah, you would be right normally, the glass. So it'd be, if we did the glass, that'd be there, but we're not going to. The cola, the ice, that's 2 of them, right? So we have the specific heat for the heat transfer for the cola, plus the heat transfer for the ice. There's one more, though. The ice has to get up to 0 degrees Celsius, right?
Nice.
Yeah. And there's the Q for the ice melting at 0 degrees Celsius. So we have the cola has to go from, what is it, 25 degrees? The cola goes from 25 degrees Celsius down to 0, right? The ice goes from negative 20 up to 0, and then it will start to melt. So there we go. All these should sum to 0. For the cola, we're going to have mass of cola, C for, we're going to use water again for this one, multiplied by change in temperature for the cola, which is going to be T final, minus T initial for the cola, which is 25 degrees Celsius. Plus, for the ice, we're going from negative 20 down to 0. So we're going to have mass of ice times specific heat of ice times the change in temperature, which is going to be the final temperature of 0 minus the initial temperature of negative 20 degrees Celsius. Plus, for the phase change, for the ice to go from solid to liquid, that's a positive mass of ice multiplied by the latent heat of it's the latent heat of fusion for the ice. The latent heat of fusion is the same for all substances within a certain class, or with all phases, so it's going to be water. Because the latent heat of fusion is for water, not for ice. And there we go, and then we just need to solve. One nice thing about this problem is that T final is 0. So this is 0, and this is 0, and that's kind of nice. So now if we want to solve for the mass of the ice, we can do some rearrangement here. Let's see if we can do this relatively quickly. So we're going to have mass of the cola, C for the water. I'm going kind of fast, so if you have any questions, can you write them in the chat about what I'm doing here? See, M cola, C water, 25. We're going to add that to the right-hand side. And then we'll divide by C ice times 20, because negative negative will be positive. And we'll also divide by the latent heat of fusion for water. And this should all be equal to the mass of the ice. Tell me if that looks right to you all. If you do the algebra yourself.
Looks good.
Okay. Next thing we need to do is we need to actually go look up the specific heat of ice. Let's do that. Alright, specific heat of ice is 2100. I was off by 10. So, just write this over here somewhere. Specific heat of ice is 2100. That is in joules per kilogram Kelvin. And we also need the latent heat of fusion of water. The latent heat of fusion for water from the table above, I believe, was like 334,000. Yep, right here. 334,000. And that's in joules over kg. We plug all these numbers in here. I think I have enough room to do this right here. We'll see. So M cola was 0.25. seawater 4190. Everything's in Celsius. We'll write these degrees Celsius on the bottom. 25 degrees Celsius. Divide by specific heat device we said was 2100. Just put degrees Celsius as well. Times 20 plus latent heat fusion of water 334,000 J over kg. That's a 4. If I could change one thing about this problem, it would be that I didn't have to do that every time I wrote a 4. There we go. Check the units. This is good advice for your test. When you're taking the test, you always want to check units. Looks like we have a kilogram and a kilogram that cancel. And then we have joules over degrees Celsius. The degrees Celsius cancels, we just have joules. And in the denominator, we have joules per kilogram, so we'll get kilograms. What do you get to calculate that? You got 1.86 times 10 to the negative 6 kilograms. Okay, thank you. Ice is 1.86 times... Can I get someone else to verify they get the same thing before we move on to the next problem? You did that one pretty fast. Y'all get anyone else got the same thing? I can do it real quick. No, I got 0.07. Oh, yeah, I got what you guys. I got what Jacob got. Check your work, Louis. Maybe something I've written here isn't super clear. That's what I got. So 0.07 kilograms, about 70 grams of ice. That's not that much ice. Does anyone have any questions? That's okay, Louis. We all make mistakes. It's totally acceptable. Okay, any questions before we do this last one, which is a little more challenging? Ah, that makes sense. I can see that. No? Alright. Alright, let's do one more. The last one. And this should kind of finish up at least this topic of calorimetry. I think there's still some stuff from chapter 17 that we won't have covered by tonight, but I think it's just heat transfer. So I would suggest that you read that part on your own. Probably won't. This will probably be like the last topic that'll show up on the test, by the way, is specific heat. So the other stuff that shows up in the same chapter, don't really worry about it for the test. So the test is actually only 2 chapters, right? It's chapter 12 and chapter 17. That's it. It's pretty good for a test, especially since it's in week 6. This class moves pretty slow because we only have like 6 or 7 chapters total, so that's how it gets divided up. All right, let's look at this problem. This is a hot copper pot. Mass of 2 kilograms is at a temperature of 150 degrees Celsius. You pour 0.1 kilograms of cool water at 25 degrees Celsius into the pot, and then you quickly replace the lid so no steam can escape. Find the final temperature of the pot and its contents, and determine the phase of the water. Liquid, gas, or a mixture. This is what makes these kind of problems challenging. Yeah, for Monday, 2 chapters, that's right. We'll go back over that at the end. This is what makes this hard. Anytime you have a problem where you don't know what the final mixture is going to be, like it could have some liquid, it could have some gas, it could have some solid, it's a lot harder. It's a lot harder. Okay, so hot copper pot. All right, so copper is this color. It's a pot, so we'll make it into like a pot, I guess. It has a spigot on the end. And what's going on? The mass of the copper. So this is copper, and the mass of the copper pot is 2 kg. We are going to pour 0.1 kilograms of cool water. Oh, and we also know the temperature. The initial temperature of this copper pot is 150 degrees Celsius, so much higher than the boiling point of water, right? So we're going to pour liquid water in here, not a lot, only 0.1 kilograms, so we'll just put a very, very small wad of water in here. And our water, the mass of the water is 2 kg. and its initial temperature, T naught, is 25 degrees Celsius. Okay? We want to find the final temperature of the pot and its contents. That's our goal. What is the final temperature? And I'm going to add one other piece to this, which is going to be how much water is left. Well, we'll just say it like this. Phase of water. Okay. There are 3 possibilities for what occurs here. There's 3 possibilities. Can anyone name one of them?
It can turn into a solid.
Well, that's probably not going to happen because it's hot, right?
Yeah, definitely.
Okay. So one possibility, that's right. No evaporation. We'll see. These are the possibilities. This is an important step of doing these kind of problems. Possibilities are, what did they say? All liquid.
Well, liquid, gas, or mixture.
Yep. It's either all liquid, mixture, and all gas. Those are the only possibilities, right? We'll say all steam. Okay. 3 possibilities. Which one is the most likely?
Liquid?
I don't know. Maybe liquid, maybe gas, maybe a mixture. I don't know.
Actually, mixture.
How would we know? How would we know? Is there any way to know?
We just gotta do
We
it.
can solve it, and then based on the final temperature, we'll know if it's a mixture or a liquid or steam, and then
You got
might
it.
have to redo the problem.
You got it. That is exactly right. So we can basically test them in order. 1, then 2, then 3. And if our answer to number 1 is ridiculous, then we go to number 2. And if our answer to number 2 is ridiculous, we go to number 3. What is ridiculous? I don't know. It'll be pretty obvious, though. Just to give you an example. Possibility 1, all liquid. If, in fact, the water does not phase change, then this is a simple calorimetry problem, right? We would just say Q for the water plus Q for the copper would be equal to 0. We plug in here MC delta T for the water plus M copper C copper delta T copper. I'm just going to use no subscripts for the water, if that's okay with you all. Mass, temperature, and stuff like that. We'll just no subscripts for water, and we'll put subscripts on this one. Now, if we do this, what do we end up getting? Well, this would work out as MC T final for the water. The initial temperature for the water is 25 degrees Celsius, right? Plus MCU CCU times delta T for the copper. So that's going to be T final minus the initial temperature of the copper was 150. And then we would just need to solve for the final temperature. And what we would get is final temperature is equal to MC times 25 plus MCU CCU times 150. We would divide by MC for the water plus M for the copper, C for the copper, and we get an answer. So what we would get here then, I'm not going to write the numbers in because we're really running short on time. You can all see what the numbers are, right? C for water is 4190. So that times 25 plus mass of the copper is 2 times specific heat of copper. We got to go look that one up. I think specific heat of copper is 490. 390, excuse me, it's 390. My memory is not what it used to be. We should write that down because we're going to use it again. So the copper, we know the specific heat of copper is 390. And for specific heat of water, we're using 4190. I'm not going to put the units on here. That looks awful. I can't do it. I almost did it, but I can't bring myself to do it. All right, so if we plug all those numbers in here, what we get is... Wait, what was the initial... I wrote something wrong. This isn't right. The mass of the water was only 0.1 kilogram. I'm sorry about that. Sorry. Alright, so, what do we get? Anyone get an answer? Are you all able to follow this if I don't actually plug all the numbers in? I had the same answer. Apparently you can't because you got an answer. Yeah, 106. Now, does that make sense?
No,
No. Why not?
because it's higher than the boiling point.
Yeah. It's higher than the boiling point. That means some of the water must have boiled off. Now, we can probably rule out number 3 now, though. Because if we got in a final temperature of, like, let's say 145 degrees Celsius, it would be probably a safe bet that we could jump to number 3, right? But because it's only 6 degrees above the boiling point, it's pretty reasonable to assume that there's not all of it has been converted, right? So I think we can pretty safely rule out both of these. We can't truthfully rule out the bottom one, but it seems increasingly likely that this is what's going on. Which, of course, is what's going on, because this is what makes these problems hard. If it was all steam, the problem would be easy. If it was all liquid, the problem would be easy. This is the only way in which these problems get hard, is when you have a mixture. So my theory on these kind of problems is you should probably always assume it's a mixture. Like, if they give you an option, it's almost certainly going to be a mixture, because it wouldn't be an interesting problem otherwise. So if it's a mixture, we kind of have to redo the problem. So what I'm going to do is I'm going to take all this stuff that we just did, and I'm just going to shift it down here so we can use all the same data that we have, and we can just write the correct way to solve the problem. So we've learned that what we set up before was wrong, and now we have to come up with a new thing to write. So now what we're going to say is we're going to have a temperature change for the water. It's going to have to heat up from 25 degrees Celsius up to 100 degrees Celsius. Then that same water is going to have to vaporize and turn into steam, some of it. And of course, we're still going to have the heat transfer associated with the copper, okay? And these should all add to 0. So this is going to be M for the water, C for the water, and then delta T for water, which is going to be 100 degrees Celsius minus 25 degrees Celsius. In fact, we now know what the final temperature is going to be. It's going to be 100 degrees Celsius. If it's a mixture, it has to be 100 degrees Celsius. So when we talk about this for the water, this is going to be the mass of steam that we end up with. So this is still water over here, but now the mass of steam, this is going to be what we're going to solve for, multiplied by the latent heat of vaporization for water, which we'll look up in the table, plus specific heat of copper is going to be, so MCU, CCU, and then delta T for the copper. The copper went from, it's going from 150 degrees Celsius down to 100 degrees Celsius. So final minus initial, this is going to be 100 degrees Celsius minus 150 degrees Celsius, and this should all add to 0. And now what we're going to solve for is the steam. The mass of steam that we have left over should be equal to, so this quantity is going to be a negative number, so when I add it to the right-hand side, it will be 50. And this quantity will end up being negative, so I'll say minus MC times 75, because we're moving all this other stuff to the right-hand side, and then we have to divide by the latent heat of vaporization for water. Let's see, so this is going to have units of joules. This is, yeah, we're going to get kilograms out of this for sure. The latent heat of vaporization for water was something like 2.2 million. To get the exact number off this data table right here, it's 2.256 million. So let's write that right here. And if we plug all that stuff into our equation right here, I think we're going to get 0.003 or something like that. That's my memory from last time. Let's see what we get. Wait. Now, I think I did it right this time. I did it wrong last time in my class. Let's find out. We'll see if I did it wrong or right. All right. Okay, copper 2 times 390 times 50 minus the water was 0.1 times 4190 times 75 divided by 2.256 E6. This is the right answer, 0.0033. So the mass of steam that we end up with here is 0.0033 kilograms, which would be about 3.3 grams of steam. And then the rest is liquid water, and the final temperature is this. All right, that's where we're going to stop tonight. We're not going to please stop. Any questions?
Oh, I think this is, like, I don't know, it just seems like a weird question because it says, like, the question is find the final temperature of the pot and its contents
Yeah.
and determine the phase.
Yeah.
So it's like, we kind of already found that, but, like, it's going to be 100 degrees
Right.
as a mixture.
Right.
So
These questions are always
I
weird
kind
like
of
that.
assumed you, like,
Mhm.
the question usually asks for the mass of this theme,
Yeah.
but, like, I assumed that, but it's just a weird.
It definitely is asking it in a weird way, I agree. I think your mastering physics problems are probably going to be a little more clear than this, like, because it's going to have an answer and it's going to be massive steam equals and you're going to put an answer in. So I agree with you. The way that they ask the question is very confusing. But it's something to take away from this, and I'm glad you asked that, is that it is very commonly the case in these type of problems where there's like the final states of mixture that you can just assume, you know, like if it's a mixture, I know that the final temperature has to be 100, right? So that's just how it's going to go sometimes with these. Sometimes finding the final temperature will be the easiest part. You just have to think, okay, what is the, you know, what's the boiling point of water, right? That's basically what we had to do here. So, but yeah. And again, the reason why it's asked in this way, to follow that up too, is because they want to kind of trick you a little bit. They want you to understand that there are 3 possibilities that you need to go through. And just as a hint when you're doing your homework, always start with number 2. The way that, by the way, if you start with number 2, you could get a ridiculous answer for this as well. Like, you could get a negative answer. That would be ridiculous, right? Yeah, so it is possible that this is wrong too, but in this case it worked out. We got a positive answer, and the number we got, it's actually pretty reasonable. This is less than the mass of water, which is good. If we got an answer that was bigger than the mass of water, that would have been a problem. So, all right, I hope this is enough to help you finish up the homework that's due this week, and to help you prep for the exam next week. Again, just a review. I'm gonna pull up the textbook real quick here. Do I have it open? I do not. So let me show you real quick what you should be studying. So there's obviously the 3 homework sets that are on mastering physics. So that's going to cover fluid statics and fluid dynamics, right? And then one chapter of temperature stuff, which basically just involves the definition of what temperature is, expansion, like heat expansion, and calorimetry. Okay. Let me see if there's any other topics in that section that I can tell you to avoid studying. So I'm pretty sure this is going to come down here and start talking about, so we got down to 17.6 right here. Calorimetry and phase changes. We didn't get to mechanisms of heat transfer. So you're going to see problems in your homework related to this. I would just recommend that you go kind of read this section right here. And we'll talk about that later on. These problems are not very hard to do, I promise you. This is very plug and chug. Okay, so just read this yourself. You can definitely learn it. We'll talk about it after the break, or after we do the exam next week. And yeah, so basically just chapter 12, and then chapter 17 up to 17.6. Y'all got it? Should I write it down?
Perfect.
Yes, please.
I'll write it down just in case. So, exam,
Do you know how many questions the exam's gonna have?
Monday night. There'll be 5, but you only have to do 4.
Are they gonna be like part questions?
There'll be parts, yeah, just like your homework.
Like homework questions or like the lab question?
Just focus on mastering physics. Okay. Focus on studying mastering physics. The topics.
On the book, I pretty hard.
Yeah, I know. They're pretty tough.
What is it called? The lab book. Those are super.
Yeah, they're pretty challenging. I mean, they're supposed to challenge you, right? It's supposed to really, and then, hopefully, the idea of doing problems that are really hard is like you do problems that are really hard, so that when you look at the easy ones, it's easy. That's why maybe even studying problems from the lab manual you haven't done, or problems from the textbook you haven't done before, is really the best way to study. Just take the textbook, flip to a problem, and just try it. That's one of
It's
the.
just setting up the problem, and knowing what to use. That's my main thing, and it's kind of like sometimes I'm just like lost completely.
I know.
When
I know.
I'm there, it's like, oh
Yeah.
really, like. So,
It's hard. I totally agree with you. That's the hardest part about physics problems is like the math is always like pretty easy to do once you've got everything set up right. So you have to focus on the setup. So that's a really good thing to say, David. It's like, yeah, you got to focus on that setup, or else yeah, I mean, it's like, where do you go? So of course I'm going to be there during the test, and you can ask me questions. You can ask me any questions you want during the test. I might say that I can't help you, or I might give you like a slight hint. I think I'm a bit of a softie when it comes to answering test questions. Like, I'm always going to try to help you because I want you to pass, and I don't want you to be confused. And I know that these things are. I know these homework problems and the test problems you'll see are so confusing. The language can be confusing. The way in which the prepositions are used, the adverbs, the verb, all that stuff can be very confusing. So, I'm always trying to help you to succeed. I don't know if you think of when you take an exam that your professors want you to fail. They really don't. They just want to write a fair test.
Some do though. Some do.
Well, I mean, they do, but I think at the end of the day, when they're grading the test, they would much rather give everybody an A if they could. You know, they'd much rather get the grade, the test back and be like, wow, they all understood what they needed to do. It's just the reality is.
One time, tell me pretty much. I don't expect you to get an A here because you should know this whole thing already. So it's kind of like for you to get an A in that course, you should have already taken it before.
Okay.
Or you pretty much studied. So that's how I approached it. Like, it's not an easy A for anyone, pretty much.
Yeah. So just to summarize the topics from the test, so it's basically fluid statics, which is, buoyancy and stuff like that. Variation of pressure with depth. Stuff like that. And then the concepts of density and that kind of stuff. And then you've got fluid dynamics, which is like continuity equation and Bernoulli's equation, basically. We'll just put Bernoulli right here. It's mostly just Bernoulli. And then, thermo stuff, which is going to be, expansion, specific heat. Calorimetry. It's not much. You really don't have to study much for this test, right? It's really not that much. So, go study hard. Don't overstudy. Make sure you get good night's rest on Sunday night before. Maybe take a nap beforehand, and try to avoid eating really junky food beforehand. Like don't eat a lot of chocolate or cheeseburgers. Try to eat healthy. You don't have to eat super healthy. You're young. Virulent individuals who can handle, eating anything. Your body will turn it into energy, but your body turns things like bananas and apples into energy a lot better than cheeseburgers. And when you eat things like cheeseburgers and pizza, you go into like kind of a crash after you do it, just like with sugar, right? Like a sugar crash, kind of same idea. So believe me or don't believe me, but if you eat healthy before the test, it actually will increase the chances that you will succeed. You all believe me when I say that? Yeah, thank you. Hope you all have a great weekend too.
Yeah, I mean, sometimes when I eat for a lot of fruit after like eating a lot of junk food, you definitely feel a lot better.
You do, right? You do. And when you feel good, you think good. And when you feel good, your brain works. So, I don't know. I'm not an expert on any of these things. I just know, like, when I was in high school, every time before a test, I would just eat a really light meal. I'd have, like, a sandwich and a banana or something like that. I used to do the same.
I overthink stuff, and then I end up ruining it. That's what kills me.
Yeah, overthinking is definitely a big problem. But, if you are overthinking something, you can always just come ask me, and I can try to get you on the right path, okay? So
we'll be in pretty much the same lab. That's what we'll be taking the test, right?
What, in the same place?
Yeah.
Yeah. So we're going to be using room 108 and 109. They're right next door to each other. We'll have a proctor in one of the rooms. We'll split you up. There'll be 15 people in each room, and that's it. I'll give you some protractors so you can use the straight edges. I'll give you paper, and you're going to rattle your answers on white paper. Yeah.
Okay, cool. Well, obviously not 15 probably, right? Because last time only like a couple of us showed up.
Oh, no. Well, that's right. This class only has like 20 people in it, so it's actually only going to be like 10 and 10 or something like that. So, yeah. Okay, that's it. Hope you all have a great weekend. I'll see you all maybe in office hours for the next couple days if you happen to show up. If not, have a good weekend.
What time is your office hours this weekend? Friday, right?
My office hours are, I will show you by pulling up Canvas. Where's Canvas? It's on the front page of Canvas when you go to our class. Tomorrow it is at 2:30 and Friday's at 1:30, I think. I always forget though. So this is 1B 1377. Right there. Tuesday 12 to 1, Thursday 2:30 to 3:30, Friday 1:30 to 2:30.
And you usually have like 1C going on, right? And all the other classes.
What? On Thursday, Friday? What do you mean?
Yeah.
I mean, 1C students come too. Yeah, yeah. It's not just two. It's not 1B, but that's okay. I mean, there's never that many students, so.
Okay. Just just like short questions or something.
What? Yeah, show up ready to ask questions because it's only an hour, right?